Hi everyone and welcome to this video series on semiconductors. So in this video series, the syllabus will be based on NTU H3 Semiconductor Physics and Devices, or NTU EE EE2003 module, which is called Semiconductor Fundamentals. Alright, so let's start with the first part, which is on crystal structure. So let's start with the fact that all semiconductors are formed with covalent bonds. For what a semiconductor exactly is, we'll look at that in the next part, which is about energy bands. But for now, let's just take silicon, which is the most common semiconductor now. So silicon has 4 valence electrons, so the bonding is something like this, where each silicon atom is bonded to 4 silicon atoms. So this is just a 2D representation. Of course, this goes on all sides. And we'll look at how the 3D representation looks like later, but for now the 2D is sufficient. So an amorphous material is where the ordered regions are very short, and the entire structure is generally very disorderly. So you can see from this, they drew single atoms here, but it's very possible that the ordered regions are within a few atomic or molecular dimensions, but overall still very short and disordered. So you can see this is how an amorphous looks like. And on the other hand, a single crystal or crystalline is where there's a high degree of order throughout the entire volume of material. So you can see this is very ordered and they are in the same direction. They are in long chains. So a crystalline material has very good electrical properties, but it's also expensive. And then in the middle, we have polycrystalline, which is sort of in between amorphous and crystalline. So you can see there are crystalline regions, which is, although it's much shorter and they might not be aligned or be in the same direction, but there's longer chains of orderly atomic or molecular dimensions as compared to amorphous, which is generally very short and disorderly. But there could be some amorphous regions like here also. Okay, so a unit cell is a small volume of crystal that can be repeated repeatedly to reproduce the entire full crystal of the material. So the entire crystal is obviously very, very, very big, and it's not very meaningful to analyze the whole crystal at once. So to look at a small cell, we'll want to look at a unit cell and often a primitive cell, which is the smallest unit cell in a lattice. Okay, so now let's look at some vector directions. So you can see vector OA is this sign, and then the final position is from 1A, 1B, and 1C from 0A, 0B, 0C. So vector OA is just final minus initial, so it's 1A, 1B, and 1C. And let's remove the ABC, we'll get 1, 1, 1. Reduction is basically trying to get all of these, if they are fractions, to whole numbers by multiplication. But since these are already whole numbers, it's just 1, 1, 1. And then we get 1, 1, 1. So that's the vector OA. And then for vector BC, you can see the final position is here, which is half A, 0B, and 1C. It's here, and the initial position is here, which is 1A, 0B, and 0C. So vector BC is equals to negative half A. Okay, later we'll look at how to write negative properly. 0B, because 0 minus 0 is 0. And then we have 1C. So reduction, we multiply all of these to make them whole numbers. So we multiply throughout by 2. And instead of writing negative inside the enclosure, we actually represent negative through a bar on top of the number. So like this, 1 bar over 2. So we can repeat the same process for planes. So what does a 1, 1, 0 plane mean? So this is actually what's called the Miller indices. Or enclosure. So the enclosure is here, it's just Miller indices. So Miller indices is the proper term. So intercepts. So we look at these intercepts, which is here. And so it intersects here at 1A, 1B. And does it intersect the z-axis? Because it doesn't intersect the z-axis, so it is infinity C. So we remove the A, B, and C, we get 1, 1, and infinity. And then we take the reciprocal, so this is still 1, 1, and then the reciprocal of infinity is just 0, so 1 over infinity is just 0. And then reduction, it's already all whole numbers, So the middle indices we get is 110 for this. So as you can see, that's the 110 plane. And then for this triangle, which they say is the 111 plane, we see the intercepts are at 1A, 1B, and 1C. And so the numbers only 111 because this is just all ones. And then the enclosure is just 111. So 111 is your triangular plane like this. So, okay, let's look at example 1.1. Sketch the crystal plane indicated by 214. And then we'll look at not only 214, but we'll look at 111 bar as well. Okay, so let's look at 214 first. So basically we work from bottom up for this one. So 214 is already the Miller indices. So we take 214 and then we take the reciprocal. We just ignore the reduction step, that's fine. So we take the reciprocal, which is 1 1/2, 1 1/4. So now we take the reduction of this, which is we multiply throughout by 4, we get 2, 4, and 1. So this is the intercepts. So x2, y4, and z1. So let's draw it. So z, y, and x. So 1, 2, 3, 4, 1, 2. Oops. Maybe I can extend this line a little bit. Okay, 1, 2, and 1. So let's just label this A, 4A, and 2A. So when we join it together, and this will be the 241 plane. Sorry, I meant 214. So this will be the 214 plane. But the intercepts are at 2, 4, and 1. Okay, let's look at 1, 1, and 1 bar. So again, 1 bar is just -1. So let's first draw this. Okay, and then let's use a different color to sort of draw a cube around it. Because you can see the 1 bar is actually minus, so it's like it will be below what your reference plane is. So let's just draw a cube first. Okay. Okay, so this is x, y, and z. Okay, so we know that this is we only need to look at 1 because it's 1, right? So if we know that it intersects x and y at 1, so it intersects x and y here 1 and 1, but the z is below by 1, so we need to move down by 1. So this is the plane. This is the 1, 1, 1 bar, 1, 1, -1 plane. But if you don't want to draw it below, below the axis and it's a bit ugly, you can just move the axis up and down. It doesn't actually affect your plane, because actually the axis is just like a reference plane, like it's just a reference. So for example, if I want the x and y intercepts to be here, that's also fine. And then the 1 bar will just be here, because relative to these 2 points, it's already 1 below. So if you want to draw the 1, 1, 1 like this, that's also fine. So yeah, essentially that's the 1, 1, 1 bar. Okay, so the three like basic structures covered in the syllabus is simple cubic, body-centered cubic, or face-centered cubic. So their short form is just SE, BCC, or FCC. So SE is just as the name implies, it's just simple cubic. So it's just 8 atoms, 1 at each corner of the cube. Body-centered cubic is just simple cubic, but it also has 1 atom in the middle, in the center of the cube. So it's called body-centered cubic. And then face-centered cubic. Face-centered cubic has 1 on each of the every 6 faces. So it has 6 extra atoms, 1 on each face, but it does not have a middle atom. So it's not like body-centered cubic. It doesn't have a middle atom. It just has 1 on each face. Okay, so let's look at example 1.1. Calculate the surface density of atoms on 110 plane of BCC and FCC, assuming that lattice constant is A. Okay, so surface density, the formula for surface density is just number of atoms on the on the specified plane or surface. So I'm just going to write number of atoms on surface divided by the area of surface. So that's surface density. And so for volume density in example 1.2, it's the same. So it's number of atoms inside the... We are just going to analyze the unit cell. So the number of atoms inside the unit cell divided by the volume of the unit cell. Okay, so let's look at the surface density of atoms on 110 of BCC and FCC. So first, how does the 110 look like? As we've seen in the previous section, the 110 plane is just this. So it's just these planes, right? And then, so let's try to draw this plane in 2D. So let's first draw the BCC one. So the BCC, so let this constant is A, so of course the rectangle is A and root 2A by Pythagoras theorem. So how it looks like is it has these 4 corner atoms, because you can see a quarter of each of these atoms make it into the plane, while 3/4 of it is actually outside the plane. So we actually only need to consider the quarter that's inside the plane. And then for the body center atom, it is fully inside the plane. So it looks something like this. And then the face-centered cubic, it's also a rectangle, also A and root 2A, and then it also has the 4 corner atoms. But then it does not have the middle atom, but it has these two half an atom, semicircle at each side, because there's the face-centered. So you can see half of this actually makes it into the face. Half of it actually makes it into the rectangle, and half of it does not make it into the rectangle, so it's only half. So if you can see, for both BCC and FCC, the number of atoms on the face is 2, because it's 1/4 times 4, because it's 1/4 here times 4 times 4 corner atom plus, okay, for this one is plus 1, and then for this one is plus half times 2, so it depends, but it doesn't matter. So it's just 2 anyways, times root 2A squared. So this is just 2 over root 2A squared, or just root 2 over A squared. Okay, let's look at example 1.2. Calculate the volume density of atoms on BCC and FCC. Okay, so the volume density of atoms on BCC and FCC. How many atoms are inside the unit cell of BCC? Okay, so if you look at this, there are 8. Okay, I'm just going to erase this first. So let's look at BCC first. So for BCC, there are 8 corner atoms. So if you imagine the unit cell, only 1/8 of this sphere of each of these atoms are enclosed inside the unit cell. So actually the volume density of BCC is equal to 1/8 times 8, because there's 8 corner atoms, but only 1/8 of each is inside. Then plus 1, because this atom is fully enclosed inside, over A cubed. So you get 2 over A cubed. So for FCC, we also have the 1/8 at each of these points. We also have 1/8, because it's also 1/8 of each atom times 8 corner atoms. And then we have half of these. Each face has half inside, right? Because if you imagine the sphere is shared between 2 unit cells, so if there's another unit cell here, this is shared between 2 of them. So we have half of these face-centered cubic face-centered atoms inside this unit cell enclosed. So it's half times, we have 6 atoms. So it's 1/8 times 8 plus half times 6, which is equal to 4 over A cubed. Okay, so now let's look at the structures of some actual semiconductors. So silicon and germanium use the diamond crystal structure, while gallium arsenide and indium phosphide and stuff like that use the zinc blende crystal structure. So essentially they are very similar. They are just derivatives of FCC. So you can imagine them as FCC crystal structure. So again, see here, consider as FCC, consider as FCC. So for gallium arsenide, you can consider as FCC with one GA and one AS atom at each lattice point. So the face-centered atom will be like this, you know, the cornered atom will be like this. And then of course this is one atom, so it's a bit hard to imagine, but essentially this is it. And then there's 4 corner and 6 face-centered GAS atoms. So yeah, because there's another like GA atom here, you know, so it's hard to imagine, but basically it is just a FCC with 1 GA and AS at each lattice point. And then it's the same thing for silicon. So instead of because silicon is a single element semiconductor, so there's a pair of silicon at every lattice point. So this and so on, and then this one is bonded with another atom in another unit cell. So for silicon, there's 8 corner, 6 face center, and 4 enclosed atoms. So you can see the enclosed atoms are this, and this. So these are fully enclosed inside each unit cell. And then there are 8 corners of, you can see quite obviously there's 8 corners, and then there's also 6 face centered, which you can see quite obviously. So that's how the 3D structures of these semiconductors look like. And this is quite important, the relative position of silicon atoms at each lattice point. So it's quite important in problem solving. So what this means is the nearest distance, or like rather the distance between 2 of these atoms are 1/4 of the 3D in 1/4 of the lattice constant. So for example, if I drop this perpendicular down to this plane like this, and then this is a perpendicular, and then I draw like this, draw like this. So if you split this in half, you'll get half A here, right? And then you'll get 1/4 A here and 1/4 A here. So this is like 1/4 A up, 1/4 A to this direction, 1/4 A to this direction, and 1/4 way up to reach the next silicon atom. So that's the shortest distance, 1/4, 1/4, and 1/4. So it's the same thing as for zinc blende, which is gallium arsenide or whatever. So 1/4, 1/4, 1/4. Then you reach it's the nearest between the AS and GA atoms. The nearest between the AS and AS atoms are just half and half. So this is half A and half A. So you can use this if they ask like, okay, what is the shortest distance between the GA and AS and something like that. So now let's try some examples. So for unit cell of silicon, A equals to 5.43 angstrom. So this is actually a unit of length. So this is actually equals to 1 times 10 to power of negative 10 meters. So it's frequently used as the lattice constant for these semiconductor crystal unit cells. So part 1, surface density of atoms of 110 and 111 plane of silicon. So the 110 plane is just this, right? So it's just this. And then you can see 2 of these also lie on the plane, and then we have 2 of the face-centered atom also lie on the plane. So the 110 looks something like this. We have root 2A and then A. So we also have the 4 cornered atom. We have 2 face-centered atom, and then we have 2 of these enclosed atoms. So the surface density is actually equals to 1/4 times 4 plus half times 2 plus 1 over root 2 times 5.43 times 10 to the power of, okay, here I'm using cm because it is popular for these answers to be put as cm, but you can use meter or you can use whatever other unit you want. So the surface density is equal to 9.59 times 10 to the power of 14 atom per cm cube to 3SF. Okay, and then we look at the 111. This is the 110. we look at the 111. So the 111 plane is, I'm just gonna erase this first. So the 111 plane is here, so 111, so it's this triangle. So you can see this 3 face-centered atom lies on this triangle. So the 111 plane will look something like this. So here are the 3 corner atoms. You see these corner atoms. So actually only 1/6 or 60 degrees, because you know what, this is an equilateral triangle, right? So we know that this is how much? We know that this is actually equals to root 2a. Each side is actually equals to root 2a. So the surface density is equals to um 1/6 times 3, which is half, plus here 1/2 times 3 over the area. Let's first split it into 2. So we look at the triangle here, the right angle triangle. So this is 60 degrees, 30 degrees, and 90 degrees. So we know that the ratio of the sides is 1 to root 3. So this side is root 2 over 2a. So we just multiply everything by root 2 over 2a. Root 2 over 2a. It's just root 2a, and then this is times root 2 over 2a. So this is root 6 over 2a. So we take root 2 over 2a times root 6 over 2 times a squared, which is equals to 5.43 times 10 to the power of -8 squared. And so this is equal to 7.83 times 10 to 14 atom per cm cube to 3SF. Okay, so look at example 1.4. For unit cell of GaAs, calculate the volume density of gallium arsenide crystal, density of valence electron in GaAs, and distance between the nearest Ga and As atoms. So let's look at the structure of GaAs. So how many atoms are there in each crystal? So there is actually 4 GaAs because of 1/8, which is the corner ones. 1/8 times 8 plus half times 6, because there's 6 face-centered. So to do this, you just look at either the As or either the Ga atoms. In this case, it's easier to look at the As atoms. So we look at the 1/8 of the As, 1/8 of the As, and then because there's 6 face-centered, so you have 1/2, because only half of them is inside. Half of them times 6, so this is equal to 4. Yeah, so let's go back to the question. So the volume density is equals to, as we have said just now, 1/8 times 8 plus half times 6 over 5.65 times 10 to -8 cube. And this is 2.22 times 10 to 22 atoms per cm cube. Okay, actually I'm just gonna write cm cube. This is 3SF. So now that we know the volume density, we can get the density of valence electrons. So there's actually 8 valence electrons in each of the GaAs, right? Because because they are covalently bonded, so there's 8 valence electrons, of course. So we have density of valence electrons is just 8 times the volume density, because this is the number of atoms, so it's just 8 times this, which is equal to 1.78. So that's the density of valence electrons. The distance between the nearest G and As. So as we have said, this is the nearest distance. So we will use like 3D Pythagoras basically to solve this. Oh my goodness. So the distance between nearest, it's not right distance, is equals to square root of 3 times root 2 over 3 times a over 4, so it's equals to 5.65 times 10 over 4, and this is equals to 2.45 times 10 to the power of negative 8 cm to 3SF. Alright, let's look at example 1.5. The figure below shows the unit cell of gallium nitride crystal, a wide bandgap group 3 group 5 semiconductor used in blue LEDs. So this is a word-side lattice with a pair of gallium and nitrogen atom at each lattice point, and an enclosed GaN atom. The bottom and top planes are rhombuses. So this is the enclosed GaN atom, and find the volume density of GaN crystal and mass density of GaN. Okay, so for the volume density, let's first see how many atoms there are per unit cell. So of course this is an enclosed GaN atom, so that's already 1. And then for the others, we can either look at the N or look at the Ga, just like the gallium arsenide earlier. So if we look at the N, you can see that 1/4 of this N is enclosed inside the unit cell, so it's 1/4 times 4, because there's 4N. Or if you look at the gallium, there is 1/8 of each of them enclosed, so times 8. So it doesn't matter which you use, the number of atoms per unit cell is 2. So volume density is equals to 2 over, okay, so what's the area? The area is of this rhombus, which, because it's 60 and 120, it happens to be an equilateral triangle. So the area here is root 3 over 2 times 3.19 times 10 to the power of negative 8 squared times 5.18 times 10. So that's the volume, and so the volume density is equals to 4.38 times 10 to the 22 atom per cm cube, 3SF. And the mass density, so we know that the volume density is this, and we know the atomic weights. So the mass density is just equals to 69.72 plus 14.01 times, okay, time this, which is 4.38 times 10 to the power of 22 over the Avogadro's number, which is this. Because the atomic weight is gram per the Avogadro number, so this is 6.09 gram per cm cube, 3SF. So yep, that's the end of this part on crystal structure of semiconductor. If you found this video helpful, please consider giving it a like and watching the other videos also in this semiconductor video series. Thanks for watching.